All right, hello again, everybody. Welcome to some more radical work here. We are going to be multiplying and dividing some radical terms here. Okay, now before we do some of these problems that I have, okay, just a couple things. It's always a good idea to have your perfect squares and perfect cubes here because we're going to have to simplify a little bit too. But then some new rules, okay, some new rules that are going to allow us to simplify these problems the way that we're going to. Okay, so the product property is the first one, and you've probably heard of this before, but basically this says if you have just the square root or just any root of something. Okay, so I'm going to just call this a square root of something times the square root of something else. Okay, basically the rule is that as long as the indexes are the same, okay, as long as the indexes are the same, if you're multiplying two square roots, the things under the radical doesn't have to be the same. But as long as the indexes are the same, you can kind of combine that under one radical, okay? So basically turning two separate radicals with the same indexes into one, okay? And then the quotient property says kind of something similar, right? You can be dividing two things, and again, as long as the indexes are the same, you can turn that into one big fraction under a radical, okay? And then we're going to deal with this in a couple minutes, but something else that we're going to deal with, rationalizing the denominator, just means that it's a rule that tells us we cannot have any radicals in the denominator as a final answer, okay? Just because radicals in the denominator leads to some weird stuff that happens, and basically, yeah, that's all I'll say right now is that that's not allowed, so we have to deal with that, okay? But that'll be later on. Okay, so just dealing with some of these examples where we are going to be multiplying and then simplifying, okay? So looking at this first one, the cube root of 9 times the cube root of 3, okay? So again, using the product property rule, right, we look at our indexes, 3 and 3. So they're the same index, which means I can multiply, right? I can turn this into the cube root of 9 times 3. And what's 9 times 3? I can multiply that to get 27, okay? And then now I think, okay, what's the cube root of 27? And again, 27 is on my list of perfect cubes, right? So the cube root of 27 would just be 3, okay? So I can simplify that all the way down to just 3, okay? So that's pretty nice that we can combine it like that, okay? Now looking at number 2, the cube root of 7 times the fourth root of 7. Can I multiply these to get some like 49 under here and then simplify? No, you might have noticed we can't do that, right? This rule only applies if the indexes are the same number, okay? And they're not here. This one's a 3, this one's a 4. So this one cannot simplify. So that can't simplify there for number 2, okay, because of those different indexes. So we just kind of have to leave it like that, okay? Now, we jump up a notch here for number 3, right? This big guy, okay? Look at they're both square roots, which means I can multiply, okay? Now, what I can do, I could write this as one massive radical, okay? And I'm going to do that, but let's kind of do two things at once. I'm going to write it as radical, but also, right, I'm going to be able to multiply across these two radicals, right? So let me do that right now, just to make it a little easier. So if I have 72 times this 10, so the coefficient times the coefficient, 72 times 10, I would get 720. Now with the x's, I could get x to the third times x, right? And that's x to the first. So x to the third times x to the first would be x to the fourth, right? Adding those exponents. And then the y's, y squared times y to the third, adding those exponents, I'll get y to the fifth. Okay. Now I multiplied that, okay? Now, probably the harder part is simplifying this massive radical down into reducing it a little bit, okay? Now we think 720, that's way bigger than the last perfect square I have listed here. And again, the list goes on, it's not just here. But so now with 720, let's deal with that first. With 720, we think about that, okay? You could make a huge factor tree and have so many numbers, so many pairs in there, okay? But what might be easier, again, is that other strategy where I said, okay, any numbers in here that are factors of 720, okay? And that might be hard. You might have to do some division, right? Like 720 divided by 4, 720 divided by something. Like I could tell you just off the top of my head, because I know 36 times 2 is 72. So 36 times 20 is going to be 720, okay? So I could write the square root of 720 is equal to the square root of 36 times the square root of 20. Okay, I could say that, that's legal. Okay, and now I could say, okay, the square root of 36, that's a perfect square. That's just 6, right? I could reduce it like that. But with 20, okay, now, because I didn't pick the biggest number I could have, I could just think, okay, 20, does that have any perfect square factors? Yes, it does, right? 4. I could say 20 is the square root of 4 times the square root of 5. Okay. And then what's the square root of 4? The square root of 4 is just 2. Okay. So kind of like a factor tree here, right? I still have my square root of 5, right? That didn't change. I can't take the square root of that. But I took the square root of 36 to get 6, and I took the square root of 2, or square root of 4 to get 2. Okay. So I could write this as 6 times 2 times the square root of 5, and combine these two. So I would get 12 times the square root of 5. Okay. And then again, I still have to deal with my variables here too, right? So just writing what I have right now, I would have 12 times the square root of 5, x to the 4th, y to the 5th, okay? And again, what we can do with my variables is kind of expand that to say, okay, I have 4 x's and 5 y's under my radical, okay? So with that, right, what am I looking for? Well, I look at my index, and that's telling me how many of a type of term that I need to pull it out of the radical, okay? So with the square root, I just need groups of 2, okay, pairs. So I have a pair of x's there, so that means 1 x can come out of the radical. I have a pair of x's there, that means 2 x's can come out of the radical, and then 2 pairs of y's, okay? So basically, coming out of the radical is going to be 2 x's, or x squared, and then 2 y's, or y squared. Okay, right, because it's 1 for each pair that comes out of the radical. Okay, and then this single y, this lonely old y, will stay in the radical. Okay, writing my final answer here, right? This x squared and y squared are going to be outside with the 12. So it'll be 12 x squared y squared, and then in the radical is going to be this 5, and then that lonely y over there, and that would be it. Okay. So that is my process of multiplying and then simplifying down, okay? Again, I would say the harder part is probably the simplifying, but again, that multiplication rule kind of makes that easier for me, okay? So that's that. Let's look at some quotient ones and some rationalizing the denominator ones, and we'll be all set. Okay, so we've got numbers 4 and 5 up here, and we're not going to have to worry about rationalizing the denominator here. You might be saying, but there's radicals in the denominator. We're going to be able to simplify that using the quotient property. If we look at 4 and 5, again, what we can do with these first is we wouldn't have to simplify any of these radicals individually. Okay, that's what a lot of kids try and do. And like you could, but it's actually just easier to apply that quotient property. Again, you just have to make sure that the indexes are the same, which they are here, and then you could turn it into a big fraction. And then simplifying the fraction once they're together, it makes it easier, okay? So 18x to the 5th over 2x cubed, right? I just take those radicands, right, those terms under the radical, and then I just make it one big fraction radical, okay? And now, look at that, I can simplify this, right? So 18 divided by 2 would be 9, right? And then x to the 5th divided by x to the 3rd, right, I would subtract those exponents to get x squared, okay? And so now I have 9x squared, okay? And so 9x squared, right, the square root of 9 is 3. The square root of x squared is just x. So that would simplify down to 3x, okay? Pretty nice with that one, simplifies very nicely. Okay, so number 5 here, we are dealing with the cube root of 162 x to the 5th over the cube root of 3x squared. Okay, so again, before you simplify anything, make sure your indexes are the same, and if they are, we can turn this into a big fraction. Okay, so I'll get 162 x to the 5th over 3x squared. Okay, turning it into a big fraction. And then I can actually divide. So you might not know, 162 divided by 3, that ends up being 54. So the cube root of 54, and then same rule, x to the 5th divided by x squared, subtract the exponents, gives you x to the 3rd. okay? So cube root of 54, x to the third. Okay, now, going to simplify this now, right? Because that's your last step, is you always try to simplify, right? You look at your list of perfect cubes, right? Because this is, again, it's really common to look over at your perfect squares and think, oh, 54 is not a perfect square. But again, it's a cube root, so you need to be thinking in terms of cubes for this one. Okay, so perfect cubes, 54 is not on there either. It's not on squares anyway, but so 54 is not a perfect cube, okay? But what I can do, kind of the same thing I did with 720 before. I think, okay, does 54 have any perfect cube factors? Okay, and 27. If I do 27 times 2, I would get 54, right? So I can break this up into the cube root of 27 times the cube root of 2, okay? And the cube root of 27 would just be 3, right? Meaning 3 times 3 times 3 is 27. So I could rewrite this as 3 times the cube root of 2. And then again, so that 2 is in the radical, now that 3 is outside, and then this x to the third is also in the radical. Okay, but again, with my rule, right, my index is 3, my exponent's 3, right? So that would be a group of 3 x's. So all of those are going to be able to come out of the radical as a single x. Okay, so the final answer to this would be 3x times the cube root of 2. All right, so that is some division. Okay, again, just turning it into a big fraction, simplifying it down. Okay, I promise this step right here gets easier with practice. I promise. Okay, so, and you can, if you don't like the steps that I'm doing with breaking it down with the factors, you can always make it through factor tree and pull out your pairs or your triples. Okay. I'm actually going to deal with rationalizing the denominator in another video, so we won't worry about that right now. But multiplying and dividing, hope those examples made sense to you. Thanks for following.